Today we're going to learn about the activity series and how it can be used to predict the outcome of a reaction. The activity series is a list of metals that are ranked according to their oxidizability, from greatest to lowest. So the most easily oxidizable metal being lithium, and the one that has the lowest oxidizability is gold. You'll notice at the lower end of the scale you have all the coinage metals, copper, silver, and gold. They're all metals that are favored because of their low reactivity, because they don't oxidize, they don't rust, they don't form oxides, or they don't easily combine with other substances. So that makes them good to as coatings for protecting other metals, or just simply as coinage metals because they don't lose their luster. On the other hand, these metals are very good for use in batteries. Lithium, as you know, is the most popular element for use in batteries. One way to memorize the activity series is to make a word out of the whole list. I put little marks here to help you memorize where the words are. Lick, Bacana, Magalman, Zinker, Econizin, PBH2, QAG, Hugpatau. That works for me. You can invent any other mnemonic that you would like that you think is effective. That's the one that works for me. So the elements near the top of the list can be oxidized by ions of any element below them. So what happens? The electrons want to flow downhill. Here's the top of the hill. Here's the bottom of the hill. The electrons want to flow this way, and the only way they're going to flow like that is if the element here is in its elemental form, meaning it has no charge, and the element below it is an ion. If you have those set of conditions, if the ion is beneath the elemental form, then the electrons will flow downwards. So let me give you an example. If you have magnesium metal and a zinc ion, zinc 2+, then the electrons can flow down, because the zinc will steal the electrons from the magnesium. Magnesium has a higher oxidation potential. It will give them up more easily. Some examples of a reaction. Single displacement reactions. We can predict whether or not a single displacement reaction will take place simply by looking at where the elements are on the activity series. So if you mix iron, elemental iron, with plumbous sulfate, lead-2 sulfate, I would like you to write the molecular, the ionic, and the net ionic equations and predict if a reaction will happen using the activity series. Here's the molecular equation of what these words represent. Elemental iron, plumbous sulfate in aqueous solution, then should turn into elemental lead, and the iron would take the place of the lead. Here's the ionic equation of that same reaction. Everything is separated, so the plumbous ion is floating in aqueous solution, the sulfate is in aqueous solution, and then what happens is after the reaction you have elemental lead and ferrous ions floating in solution with sulfate. If you eliminate the spectators, the parts of the reaction that are the same before and after, then you get the net reaction. And the net reaction is that elemental iron will react with plumbous ions to give you elemental lead and ferrous ions. So this reaction does take place because the lead is beneath iron. The lead ion, the plumbous, is lower on the hill than the iron in the elemental form. So the electrons can flow that way. They will flow towards the ion and reduce the lead while oxidizing the iron. So these elements that are higher up on the hill are more easily oxidized. They more easily give away their electrons. In the next example, we have bromine reacting with sodium chloride. And in this reaction, there is no reaction. Why? Because bromine is a non-metal. And when you have a non-metal, non-metals don't like to give up their electrons. So they're not going to give up their electrons to a sodium cation. Sodium is high up on the list as well. It doesn't like to give up, it likes to give up electrons, so it's actually quite stable in the form of a sodium cation. So no reaction for that particular combination of substances. When you combine magnesium with cupric chloride, CuCl2, here's the molecular equation, and according to the activity series, if we go back and look at the activity series, we see that magnesium is over here, and the cupric ion is way down here. So yes, the electrons can flow downwards. So this is a reaction that will take place. The elemental magnesium will react with the cupric chloride to give you magnesium cations, and the iron, the copper will return to its elemental form. Here is the ionic equation where everything is shown in the form of ions. Here's the cupric ion, here's chloride. Here's magnesium 2 plus after the reaction, and here's chloride again, and the copper turns into the elemental form. When you eliminate the spectator ions, here's the net reaction. Magnesium metal reacts with cupric to form magnesium cations and elemental copper. Again, with copper and silver nitrate, we have elemental copper reacting with silver nitrate. Here is the representation of it in a symbolic form. Copper solid, which means elemental copper, reacting with silver nitrate, should give you cupric nitrate and elemental silver. If we go back to the activity series, we'll see that copper is higher up than silver. So as long as the element is higher than the ion, then the electrons can flow in that direction. And in this case, we start off with elemental copper and Ag+. So the electrons can go from the copper to the silver. And in the net reaction, we'll notice that the elemental copper has reacted with the Ag+ to give the cupric ion and elemental silver. With calcium and hydrogen chloride, the reaction would result in the formation of calcium chloride and hydrogen gas. As we know, this reaction does take place. And if we go back and look at the activity series, we will look at calcium. Oh, here's hydrogen, here's calcium. Calcium is way higher than hydrogen. And we have elemental calcium reacting with hydrogen ion, H+. So yes, the electrons can flow downwards to the hydrogen, and the hydrogen will be reduced to give hydrogen gas. The result is that here's the ionic equation. We can eliminate the spectator ions to give the net equation. Calcium, elemental calcium reacting with hydrogen ions to give calcium cation and elemental hydrogen. The next thing I would like to ask you is a simple Fermi question to help you improve your mathematical abilities. And the question says this: assume the Earth is 7,926 miles in diameter, that it's composed of 2/3 water on its surface area, and that the oceans are an average of 2 miles deep. Also, water has a density of 1 gram per centimeter cubed. How many molecules of water are in the oceans? Now, to solve this problem requires you to understand, to develop a rationale for finding out the volume of the ocean. One of the ways of finding out the volume of the ocean is to find the volume of the entire Earth and then subtract the volume of the Earth without oceans. The difference between the volumes of those two spheres will give you the volume of the oceans. The Earth is 7,926 miles across, and the average depth is 2 miles. That would mean that the inner diameter would be 7,922, because you've subtracted 2 miles from both sides. So now the diameter is reduced by 4. With this assumption, we can say the volume of the sphere is 4/3 pi r cubed, which means we can write the following mathematical simplification. Let's turn the radius into 7,926 miles over 2, because we have the diameter. So divide the diameter by 2. And if I want to subtract the volume of the outer sphere, of the inner sphere from the outer sphere, so that's what we're going to do. Here's the volume of the sphere, 4/3 pi r cubed. And here's the diameter of the inner sphere divided by 2 to give the radius, and then we cube both those quantities. We can simplify this by factoring out 4/3 pi and simplifying the number. 3,963 cubed minus 3,961 cubed is going to give you the following: 4/3 pi times 9.4184 666 times 10 to the 7 miles cubed. That number simplifies to 3.9451 9806 times 10 to the 8 miles cubed. And then we're going to multiply by 2/3, because only 2/3 of their surface is actually covered with water, and it reduces the number down to 2.63013,204 times 10 to the 8 miles cubed. Now, of course, you can see that the nature of this calculation is very rough, but that's precisely how some calculations have to be done. It's a ballpark, but the power of Fermi questions is that they help you to develop analytical thinking, and they can bring you to a pretty close estimation of what the number would be. Now that we have the volume of the Earth's, all the Earth's water and all the oceans, we can convert it into centimeters cubed by using the appropriate conversion factors. We're going to multiply by the number of feet in a mile, which is 5,280. But we'll cube the whole conversion factors because remember we're working with volume, and volume is made up of length, width, and height. So it's 3 dimensions, so your conversion factor has to have 3 dimensions. Then we're going to convert inches into feet, cubing that factor as well. And we're going to convert inches into centimeters with this conversion factor, where there's 2.54 centimeters for every inch. The result is, I'm going to multiply all those numbers through, 1.09686 times 10 to the 24 centimeters cubed. Keeping in mind that density is equal to mass over volume, and therefore density times volume is equal to mass, we can enter this number here in volume. The density is 1. I'm just going to do that here because I'm running out of room. We'll get that the mass of the water in grams is the same as this number, 1.09628686 times 10 to the 24 grams of water. Now, if we divide by the molar mass of water, which is 1 mole per 18.01528, is that right? Okay, that's the molar mass of water. We get, there are 6.0853 times 10 to the 22 moles of water. I had to cut off the decimal place there as I wrote it on the board, but I did keep it in my calculator. I'll continue the calculation here because I've run out of room. Take that number, 6.08 times 10 to the 22 times Avogadro's number of molecules per mole, and there are 3.66 times 10 to the 46 molecules of water in the ocean. Any questions?